Yeah, so welcome everybody. Good afternoon here in beautiful Amsterdam. I must admit it's for me the first time being in Amsterdam, which is really strange because you hear from my accent, obviously I'm a German guy. I live nearby Cologne, which is just a 3-hour ride. And yeah, I'm already today, I know I will be back because it's such a beautiful city. Steve, thank you for the nice introduction. You actually spared like 5 minutes of my introduction on what is edge computing and what are the use cases. So we can spend a little bit more time on the pretty nitty details on what it needs to bring a Kubernetes distribution to the really small edge device. So my name is Daniel. I work for Red Hat since I think 7 years now. I used to be in sales, working a lot in OpenShift sales, selling Kubernetes to standard IT customers. And recently, I transitioned into the product management role. So I'm actually a product manager at Red Hat. And as you see in the slide, Red Hat has been born 30 years ago in the traditional data center. And yes, we just celebrated 30 years of surviving with open source in the IT space, which is, I think, quite an achievement. I'm proud of that. So after winning the data center, we went into the cloud. Hybrid cloud is obviously a big business in the last 10 years now. But recently, we extended to edge. And as Steve said, edge computing use cases are, from my personal definition, really easy. If you do any kind of compute, not in your data center, not in your cloud, but anywhere else. Yeah? It could be a really small edge device running in a point of sale, point of information solution. It could be a cruise ship. It could be a satellite flying around the Earth. I'm now since like 5 to 4 years in this edge space, and if I learned one thing, then it is no one size fits all. Yeah? Everybody has different requirements, different sizes, really from 2 cores, 2 gigabytes of RAM, just a Raspberry Pi, Intel NUC type of device, ranging to server grades up to, hey, actually it's a big rack and it feels like a data center. It has like 200 cores, but still it's on a cruise ship, right? So, and because it's disconnected, I would count this as an edge device. So, the more aspects are like the connectivity, power consumption, that are criteria. If you are constrained in any kind of these domains, that is already kind of an edge deployment, right? And it could be power consumption, for example. Yeah, think about a flying drone. Think about an oil rig where you have just solar power, yeah? Where, for example, ARM is really good because it has a nice power to compute ratio. So, but still, I mean, this is not really new. We have been doing point of sale solutions in the last 20 years already, right? So cashier, something like that. So what brings us to the game? And that is that we want to apply cloud-native principles, cloud-native technologies to these types of edge locations, right? Because I try to avoid the word cloud-native applications because I'm at the edge, I'm not in the cloud, go away. I prefer to use the word modern application development, yeah, where you have like microservices, event-driven architectures, to get all the goodnesses you get from cloud technologies, like resilience, like doing upgrades while you are in production. Yeah? And we want to apply these types of technologies also to edge locations. And that brings us to Kubernetes, right? Because one of the primary cloud technologies in the last 8 years, how old is Kubernetes now? That's one of the major cloud technologies, and we want to use that for at edge locations. And that is what I'm going to talk about. And to give you an example on what I'm talking about or meaning is, let's take a look about the brief history of Red Hat's Kubernetes distribution, the upstream community project OKD or OpenShift as the enterprise supported product. And here you can see the trajectory on how we reduced it. Yeah, when I started like 6 years ago with that, we were on a trajectory like you have a minimum scale of 9 servers you need. Yeah. And it has to be physical servers anyway, yeah, then getting virtual ones even is really big one, yeah. Remember here, external etcd, that was the reasons why we needed 9 nodes, yeah? 3 for the control plane, 3 for the etcd, and then 3 for the workload, which is, by the way, an insane ratio of overhead to what you can actually use with the platform. So then we started slowly on a trajectory to reduce our footprint from 6-node clusters where we removed the external etcd, getting to compact clusters where you just have 3 nodes, where you have control plane and worker nodes in the same, and then even getting smaller and smaller. And that was mainly driven by telco edge computing, yeah? Because in the telco use case space, where there's a big trend to move away from bespoke specialized network equipment to standard IT equipment and just run everything software defined. And we had early customers pushing us into that, but you have to reduce the footprint because it's just 3 servers. Now it's just 1 server where we have single node OpenShift. And then this trajectory somehow continued, and customers pushed us to, yeah, we want to run Kubernetes, but not on a 12-core single server. It has to run on a, let's say, Intel NUC with just 4 cores. And yeah, that made us look into this and how to approach it. And actually, I'm the product manager for these 2 products here, looking at the requirements and shaping the roadmaps for these. Before we jump into the details on how we did this, let's talk about the elephant in the room. Why on earth would you like to do Kubernetes on a 2-core system, right? Single node, single point of failure. Why? I mean, think about it. What's the heart and essence of Kubernetes? That is, take a lot of workload and schedule it to a lot of nodes, finding for this workload, this pod, where on earth do I fit this in over there, right? And now I'm on a single node where, hey, there's no question where to schedule it. Use the one you have, right? It's so small. Why on earth would you like to do that? And the answer is quite simple. Users want to use cloud principles, these modern microservices architectures, event-driven, DevSecOps principles also for edge computing. Or there might be an ISV having a solution for point of sales, for example, for manufacturing execution systems. And these ISVs face a challenge of being able to run their workload from software as a service in the cloud, where they use maybe GKE or EKS or whatever, yeah, to another customer has it on-prem in their private data center. And yet another customer says, yeah, I want to run it on a really 2-core system, small edge device. It's just an, let's say, for example, just an IoT gateway, yeah, where you connect data. So you would like to use the same principles, the same technologies, methodologies like your CI/CD chain, and use the same Helm charts maybe to deploy your workload even to the edge location, right? So that might be a good reason to run Kubernetes on that, yeah? And all the goodness of, for example, just a rolling update. If you think about, for example, if you just use Docker or Podman on a single node, you're a little bit in trouble on doing a rolling update while the system is running. You can do that, but it's much uglier, it's much more complicated. That's what Kubernetes is really great at, right? And still, you need to add the additional stuff like ingress routing, security certificates, and so on. So actually, there are good reasons, and you have to balance that. Yeah? And that is why at Red Hat, we decided that we actually approach this and tackle that. So there's a big difference between where we are coming from, the traditional OKD, OpenShift, single node distribution, which you can see here on the right-hand side, which is a full-blown Kubernetes distribution. The design approach of that is we take the whole platform and put it on a diet. Make it slim, remove components you don't need, remove, for example, all the scaled-out deployments, reduce it to 1, but still, it is a full-blown distribution, and the design philosophy is it walks, quarks, and acts like the full-blown thing. So everything you have, you're familiar with OpenShift, like the console, everything is there. Yeah? And that brought us to a dilemma, because the minimum system footprint of the regular OpenShift Kubernetes distribution is 4 cores. And out of these 4 cores, you can utilize probably 2, because the rest is used by the etcd API, something like that, yeah, and much more RAM. So To get into this really 2 gigabytes RAM, and you can actually do something usable with that, we had to switch design approaches, yeah? And that is why we started on the left-hand side with Microshift, where we basically, the design approaches, we start with nothing. Then we take the absolutely minimum Linux distribution we can think of, and then we add just the layers and pieces you need to run your Kubernetes workload. That's the design goal, that we have Kubernetes workload portability, that the same workload you run on your full OpenShift cluster, you can run on the Microshift cluster. Yeah? That's basically the idea. So start with nothing, and you can see a lot of differences. For example, here, it's just networking, ingress, storage, and that's basically it. All the rest, like monitoring, logging, and so on, is not there because you don't need it, right? So it's really the bare minimum approach, and every time we add anything to this distribution of Microshift, we think about how big is it, how much CPU does it consume, how much RAM does it consume, can we afford, do we want to afford it, does every customer need it, do we have to make it configurable that only the customers who really want it get it, stuff like that. So in the next couple of minutes, I'm talking only about Microshift. And these design decisions we made to build this Kubernetes distribution. And once you have the very basics, like, okay, you need where to store the Kubernetes state, we use etcd for that. That was for us kind of a no-brainer because that's the one where we have biggest experience in, so we keep with that. The really next thing is the networking provider. The CNI implementation. What's your CNI driver you would like to use? So here you can see we have come up with a couple of requirements we need to take a look at. For example, the footprint, as I mentioned. What's the CPU, RAM consumptions? But there are other requirements, like, for example, this dynamic IP requirement, which is a little bit unusual. For example, especially if you're coming from the telco edge, if you think about a telco 5G base station deployment, that doesn't change its IP addresses. Yeah, it has nice network addresses, everything's fine. Now, if you think about a, let's say, train, you have an edge device running in a train moving around, it switches networks, it switches IP addresses. So you have to support dynamic IP address changes. Yeah, which is in the data center cloud, it's not that often. Yeah? And the devil is really in the details, like your network provider has to be able to cover with that, but also the surroundings, like, for example, have you thought about certificates? Oh, yes, there are internal certificates because the internal communication is secured. So you have internal certificates, and there might be the IP address in there, so you might, even as a side effect, be able to recreate certificates. So, and then, of course, we have requirements like we have to be able to support it, supportability, because at the end, we are making money of this by providing enterprise support for this. So can Red Hat as a company support this technology is an argument. But also other requirements, for example, is there the network policy support for CNI networks if you want to isolate between namespaces, stuff like that. So lots of different requirements, and then so we took a look into the different providers or implementations and did an assessment. Like, for example, we did measurements of the footprint. How much CPU RAM does it use? Yeah, and for all the rest. And so here, for example, the obvious outcome is we choose OVNK. Yeah, besides, yeah, footprint is a little bit higher, but all the rest is green. So Microshift uses OVNK as a CNI provider. Yeah. Same questions, same problems arise around, for example, storage. Frequently we get the question, hey, why storage? We are talking about modern applications. They should be stateless, right? Why do I need storage at an edge device? Welcome to reality. Steve told us it's about data at the edge. You might be not allowed to transfer that data into the cloud. You might not want to transfer it into the cloud. Still, you have to store it. Think about, for example, time series database. If you have the ultrasonic data from your example, or if it's temperature curves. To do this predictive maintenance digital twin type of use cases, you might need to store at least the last week of data. And you have to do this on disk, right? Because a reboot might happen, might be a power outage, so doing this in RAM is not a good idea. So yes, having a CSI, container storage interface provider, is a good idea. even on a 2-core, 2 gigabytes of RAM edge device. But it has to cope maybe with only 16 gigabytes of SD card, right? So, yeah, and again, we did the same. We had requirements like it has to be run unprivileges. Here, it has to enforce storage size requests. That was a really important one. That is, if you have 2 ports and they store data via their persistent volume claim into a PV, you don't want that if port A is misbehaving and consuming all the storage and filling the data, you do not want to have that an impact to the other port. Yeah, that should be isolated. But if you do really simple host path provisioning, oh, sorry for the abbreviation, HPP is host path provisioning. So what you simply do is you map that storage PVC claim from the port to the file system of the host. If you do that, there is no isolation because it's just a directory, yeah? And in that directory, they share everything. So there's no isolation, so that's not a good thing. Yeah. That's here, protection against greedy workloads. Support snapshots. CSI snapshots are important because that's the entry point for each and every Kubernetes backup and recovery solution. Because the data might be valuable, so you might want to have backup and recovery solutions for that in place. So, yeah, we actually did the same ARM support. That was also a fun surprise. Because obviously at the edge, ARM is a good idea. And so we did, again, our due diligence, and in this case, we decided for our variation of Topo LVM. It's an upstream project which simply maps persistent volume claims, persistent volumes, to logical volume manager logical volumes. If you're familiar with Linux, there is this LVM thing, which is quite flexible in providing storage, and it's really nice because it has dynamic provisioning, and we have actually an enterprise supported version of that at Red Hat, so that was an easy one. Yeah, talking about another really challenge at the edge is you do not want to brick your edge device. Yeah? We have customers who run this stuff at a location where if you need to get physical access, you have to fly in with a helicopter. That's expensive. You really want to avoid that. Now, how do you do an update consistently, transactional, without bricking your device? And the simple ingredients for that is, first of all, use OS tree. OS tree is a different deployment type of Linux where you have kind of an immutable operating system. So it's not RPM-based. You install your packages at that device, but you, on your development environment, build the distribution. You build your image, your commit, and there's everything baked into it, and then you just deploy that to your edge device. Yeah? It's kind of a change from a package-based to an image-based deployment. Yeah? That is something we have in Linux for quite a while out there, which is good because it brings you this atomic update capability. So on a single edge device, you can have 2 of these different commits, version A1 over here, and maybe then a version H2. You stage that, you download that. First you download it, so you have 2 versions parallel. This one is active, and then you do a reboot into the new one. So both images are on the same disk, and you boot your system into the new one. And if everything is fine, if all the health checks turn out fine, you are on version A2 after that. And if something is going wrong, yeah, if your workload is wrong, you added a wrong patch, the security patch is not compliant with that hardware, your workload did something stupid, you can easily roll back by simply doing a reboot into the previous version. It's still on disk. You can do that. So that is a really nice feature, which is out there as OS tree-based deployments for a couple of years. Now we add Kubernetes to that, which makes your life a little bit more complicated because you could imagine that from version A1 to version A2, you actually have a Kubernetes update in there. So your etcd database might change, the physical layout, the API might change, all that stuff, and now you roll back. So you have to do a rollback of your Kubernetes distribution. And that is for us, for example, in product management and engineering currently, hence the work in progress sign here, quite a challenge. And that is what we are currently focused on to get this right, because that is one of the big differences between our small Microshift Kubernetes distribution and the full-blown OKD distribution. The OKD distribution never ever rolls back. It's always path forward. Here we have to learn and find a way to consistently roll back and get into the previous state. And we do this actually by doing clever backups and restores. So we capture, for example, the etcd database, bring it to a safe location, and once we roll back, we restore that. So with that being said, I think networking is also a topic. That's the last one. So this has to work in a fully self-contained air-gapped networked environment. Like, for example, your edge device might have not a connection at all. And yes, we have customers with a requirement. You walk up with an USB stick to that edge device, plug it in, turn it on, wait, and then after, let's say, 60 seconds, 2 minutes, the whole workload is up and running. How do you get this done? Usually you pull all the images you need from your registry and so on. And here the idea is that in that OS tree commit that you build, it's literally everything you need to run your workload is baked into that, even your container images. Yes, we configure the runtime in a way that you have actually 2 container image locations, one for the static immutable part of the OS tree commit. Keep in mind, OS tree commits are immutable. You cannot change them after you have built them. And then you might later add dynamic ones, so we have actually both storages. And that is what you hear in this image builder blueprint declare. For example, for Microshift Offline, you describe here, for example, the Microshift package. This actually brings you the Microshift installation to your edge commit. And then you can declare all the container images. Like, for example, where do you want to get these container images from? So now at image build time, all these images are being pulled. And yes, we provide, for example, for all the internal images Microshift requires for the router, the networking, and so on. We provide the necessary locations where to find them, so you can bake them in. And then you have all really fully self-contained there. You can just turn the device on and it works. I could talk for hours about this. I had no time to talk about, for example, security. One of the really, really big challenges in edge computing is security, especially if you can't guarantee the, let's say, physical integrity of your device, if you have to live with the fact that it can be stolen because it's sitting out on a parking lot in just a big display, stuff like that. How do you handle private keys? I think we have a session later for that on how to handle that. It's not that easy. So with that, I think I am kind of done with what I wanted to say all about this. I will be here for the rest of the day. I will be here for the rest of the week. If you have questions, comments, please feel to reach out to me. Daniel Fröhlich at redhat.com is my email address. So thanks for your attention and looking forward to the rest of the sessions.